Good morning. Hi, y'all. We're going to be looking at section 9.1 today, all about finding the area between two curves. So I thought the first thing we could do is just watch a little animation of how we could find the area between two curves. So what you're looking at here is some cube root of some x minus 2 plus 3 and the sine of x plus 1, and we're just looking at the graphs of them. Okay. And the question would be, what is the area between these two curves? Right? So what is the area between those two curves? So right now, I don't know if you can tell, it was integrating along this top function, right? So it's trying to fill in, all that green is looking at the, the definite integral. So it'd be, the space in between that curve and the x-axis. Now the second one's going with the second function, and that's the red piece that you're seeing there, right? That's the area underneath that curve. And then hopefully you can connect that remaining stuff that's in between, that's what we're looking for. That would be the area between those two curves. So now what's being drawn in that purple is what we're trying to come up with. Okay. So if you can imagine, did I pause it? Nice. So if you can imagine this idea of what we want to do is, kind of think about, if you can imagine if I stopped it, I paused it right here. If I asked you what this distance is right there, we could hopefully imagine that that's like a y distance. So I went over some x distance and I went up some y distance, up to whatever that top function was. And then I'm going to subtract out wherever I was on that bottom function. So you're going to hear me say this a lot this unit. I'll be like top minus bottom, top minus bottom. That'll be the length. For that slice right there, it was that curve minus that curve, right? Over here, it'll be top minus bottom, top minus bottom. Now we're not actually going to add them all up. That's what calculus is for. It integrates as we go. Right, but that's the idea of what we're doing. So there's a very formula, related with the area. You'll think about integrating the top function minus the bottom function, starting at wherever you started, and then ending wherever you ended. So it'd be like the integral from a to b of the top function minus the bottom function. Okay. Any questions, comments so far? Okay, now I'm going to switch back to actual math. Let's see how this goes. Okay. Okay, good. Here it is. So let's do some math. And so here's our first example. This one we can actually do without a calculator, which is nice. And so, let's first say, if it says a definite integral, I see what I'm saying. Okay, definite integrals, y'all. Is it possible to get negatives out of definite integrals? Start again. Is it possible to get a negative out of a definite integral? I know it's been a while, but if you integrate, if I have this function here from a to b, and I take the integral from a to b along f of x, yes. Am I going to get a positive or a negative out of this? Negative. This would be negative, right? It'd be beneath the x-axis. So a definite integral, you can get a negative, right? So can be negative. Similar to displacement, right? Displacement and distance. Displacement can't be negative versus distance can't be negative, right? Similarly, if they say, hey, find the area between these two curves, we're always getting a what out of that? Positive. Because literally, how much space is sitting here? It's going to be a positive value, right? So between two curves, always positive. So always positive. You don't care whether you're above the x-axis, below the x-axis. You're caring about the top curve and the bottom curve, and you're figuring out how much area was living there. Okay. So far I've only been talking about vertical slices, like top minus bottom. There is the harder of the two, the horizontal slice. So I'll show you both of those today. Okay. But main idea, find the area in the first quadrant only for this problem, which is nice. So we've limited it, right? Between the curves f of x equals x over 2 and g of x equals 2x. Okay. I'm going to model this one first like it's no calculator, and then second like it is a calculator question. So first, no calculator. To figure out where these two graphs cross, we'd want to set them equal to each other so we can find the points of intersection. So to find points of intersection, right, you can set the two graphs equal to each other and solve. So set graphs equal and solve for x. Right, so when does f of x equal g of x? So when does x over 2 equal 2x? And I know we're in calculus and this algebra is going to be tough for us, but we can do it, y'all. We got this. So let's solve this for x, right? Well, what would y'all do to both sides? Multiply by 2, get rid of that fraction. That's what I would probably do as well, yeah? So x would equal 4x. Now what? Subtract the x over, sounds good. Subtract the x over, so 0 equals
3x and then divide by 3.
And now I'm like, man, I think I have an error on this. Sorry, video. I'm like, I want more than one point of intersection. I think I forgot a squared or a cube. That's what it is. Okay, it's cubed. So x cubed over 2. Let's try this again, y'all. My bad. X cubed over 2. Double check my notes before I start filming. Is what I meant. Much more interesting problem, right? If it was just x over 2, that would have been a line crossed with another line, and they would have just had one point of intersection, right? As I was solving, I was like, wait, I'm only getting 0. That was not what I wanted to do. So let's try this again. What if it's x cubed over 2? I still like multiplying both sides by 2, right? But now we'd have x cubed equals 4x. So now what should we set equal to, or what should we do? Not ready to cube root yet, because we want to set equal to 0 and like factor, right? So subtract that 4x from both sides. So you'd be like x cubed minus 4x would equal 0. And now what can we factor out? X, nice. We'd be left with what? X squared minus 4? And x squared minus 4, x plus 2x minus 2? This is what I was expecting. I was like, wait a minute, that's not seeming right. So now we have multiple points of intersection, right? X equals 0, x equals negative 2, x equals 2. Now on this one, they did have that caveat. They said only in the first quadrant. So we're not going to worry about one of these points of intersection. Okay. But let's say you had no idea what these graphs look like. You could still do that algebra on the page to solve if it was solvable by hand, right? If not, you're going to do that work in your calculator, right? So this is by hand. If not, you're going to graph the first equation and the second equation and find the points of intersection in your calculator, right? So with calculator, you're going to graph, and so you'd be like y1 would be your f of x, you know, your y2 would be your g of x. You'd graph, and then you'd second trace calculate. I think it's 5, the points of intersection. So you go second trace, right, which is calculate. I believe it's 5 intersection points, and so you'd find the exact points of intersection. This is where, depending, obviously these functions are like super clean, but sometimes the functions will be really messy, and this is where storing the points of intersection can be really helpful for later in the problem. So if they cross at really messy decimals, maybe you'll save the first one as A, the second one as B, and then just use A and B for the whole rest of the problem. Okay. So that's the first step, is like finding the points of intersection. Okay. On this one, let's go ahead and do a rough sketch. Maybe I would challenge you to graph without a graphing calculator, just to see what you remember, right? X cubed, I hope you have a like idea of x cubed. And then dividing by 2 is just like a 1/2 out in front. Just like a multiplier, it's like gonna scrunch it, you know, compress it towards the x-axis. And then 2x would just be a line. So hopefully you can get this idea that it would just be a rough, you know, here's my x cubed-ish, ish, yes, and then y equals, or g of x equals 2x. So 2x would just be a line, right, going through the origin. So the slope of 2. So, and so hopefully you can see those points of intersection, right? Boom, back here, there's my negative 2, right? Boom, there's my 0, and boom, there's my 2. So if they hadn't said, find the area in the first quadrant only, we would technically have to find this area and this area. And remember, they would not cancel out in the same way that definite integrals would cancel out. They would just like, it would double. It would be like whatever that shape is the same shape, and there would be 2 of them. But in this case, we were only worrying about this piece right here. So I'm just gonna draw that a little bigger so we can like work with it, but that's the region that we're working with. Questions, comments so far? Okay, and so I'm gonna re-sketch over here. This region here we have, so let's see, and my black pen is f of x. So in my black pen is f of x, and then my red pen is going to be g of x. And I hope you can see that. But in this case, in this region, to do what we would call vertical slices. So we want to imagine, like, no matter where we slice this, what this distance was, right? And we're starting here at 0, and we're ending here at 2. And so the formula, if you will, for like the area, to add up, you know, that slice plus that slice plus that slice, we'll use a definite integral, because that's what definite integral is, right? We're summing up all the things from here to here. So the kind of formula, if you will, for a, what we'll call a vertical slice, right, would be the integral from wherever we started to wherever we ended, so the integral from A to B, along whatever curve is sitting on the top, minus whatever curve is sitting on the bottom. Yes, question?
Could you also not just find the area of the semicircle for this problem, or would that not work?
Ooh, I think you've assumed it's a semicircle. Just be careful. We don't know for sure that it's a semicircle. So that curve, you know, is x cubed, but that doesn't necessarily mean that it's an actual semicircle. You know, to our eyes it might look like it, but we can't assume that. That's what's so nice about those problems on the free response, where they print, hey, this is a line and a semicircle, and then you're not assuming, you know that it's a semicircle. Good point. But it's probably pretty close to a semicircle, you know? And then whatever letters this is with respect to, like I don't know if you can see that we're starting at, this is an x value, x was 0, and this is an x value. So these would be with respect to x, this would be a dx, you know, and this is going to be x equals some a value, x equals some b value. So for this specific problem, right, we were starting at 0 and going to 2. So we're integrating from 0 to 2. The top function was g of x, right? That was our line. So I could just write as g of x, minus the bottom function was the curve. I could just write that as f of x. And then all with respect to x. So this would count as like my setup on a test. Like this is the area between those two curves. So the area between those two curves would be the integral from 0 to 2 along g of x minus f of x. And big idea, like what I showed in the animation to begin with, the integral of g of x, right, would have been all the stuff beneath the red line. The integral of f of x would have been all the stuff below the black curve. And that's why the integral of g of x minus f of x is the difference between those two. And we just tend to put them all in one integral. Now, because we can do this by hand, you know, we can do this by hand. I could write g of x right here, 2x, minus f of x, and I could put x cubed over 2. However, I'm afraid if I do this by hand in the video, we're gonna get so into like the weeds of solving this problem by hand that we're gonna kind of forget the big idea. So sorry, here in the video, I'm just gonna show using our graphing calculator, but this would be a problem we could antiderive by hand. I hope we're clear on that, right? Because you could take the antiderivative of 2, the antiderivative of x cubed over 2, say evaluated from 0 to 2, plug in the top 2 minus plugging in the 0. That's called the fundamental theorem of calculus. So super important. Let's just go ahead and grab our graphing calculators and type that in. So again, if you had a big old free response on this, maybe you would want to type in for your y1, you know, maybe the top function. So x to the third divided by 2, and maybe your y2, whoops, can't see it at all, huh? Would be 2x. Make this a little darker. And then you would do math 9, right? We'd integrate going from 0 to 2 along y1 minus y2. So you'd quit out of this, and you'd be like math 9, integrating from 0 to 2 along bars, y bars, y bars, y1, minus bars, y bars, y2, and then with respect to x. Ooh, I must have done it backwards, huh? It's a good lesson to learn. So I typed in my y1. Look, I got a negative, right? I typed in my y1 just in order, and look, that was my cubed, right? That was not the one that was on top, that was the one on the bottom. So let this be a lesson, Miss Mills, be careful in the order that you type it into your calculator, right? Now you're pretty much, like if it was multiple choice and you get that answer, you're pretty safe to pick the like positive 2. You're like, oh, I might have missed the order, right? You might have missed the order here. You might have also put the limits in wrong. So that's another way you could have gotten a negative accidentally. But let's just fix that here. So if I go second enter, it'll pull up what I just typed in, but I just want to, I'm going to delete my y1, I'll delete that negative, and in here I'm going to insert So I'm gonna go second insert, I want a minus y1 instead. And now if I press enter, there's my positive 2. Again, we could have done that problem by hand, and we would also have gotten a 2. Okay. Questions, comments? So while we're here on this same problem, we're gonna do the same problem, a horizontal slice. Okay, so this is always harder, and for areas, y'all, they'll never force you into an orientation. Areas, you will always have the option to slice it vertically or horizontally on your own. But when you get into volumes, they're forcing you into an orientation. So they're gonna say, hey, you gotta orient it, revolve it around an axis like this, or you're gonna revolve it like an axis like this. So they'll force you into horizontal or vertical. For areas, they never force it. So traditionally, verticals are easiest. I'd say 90% of the time, I'm gonna use a vertical because horizontal is a lot more work, okay? But we can do this one both ways, so I do wanna show it. So a horizontal slice, so if we have that same shape, right? Before we were slicing it top minus bottom, top minus bottom. I don't know if you can see if we do a horizontal slice, we can go right minus left. I can go right minus left. I could just slice it this way and I could just add up all those slices. Starting from here, which I hope we can tell is 0, right? This one was 0, and we plugged in 0, we were at 0, right? Now this one over here was 2. What will this point of intersection be if our x value was 2? Plug in 2 over here, y'all. What is 2 times 2, or 2 cubed divided by 2? It's gonna be 4, yeah? Nice. So if we slice it horizontally, that's the first thing you have to think about, is that your limits of integration are gonna be in terms of y. Okay, so this is the generic formula for a horizontal. So a horizontal formula for area, again, is then that you're gonna be integrating. These are gonna be y values though. So you're like y equals a to y equals b. And then instead of top minus bottom, and top minus bottom is just because the bigger numbers are always up top and smaller numbers are always on the bottom, right? So on horizontal, we're gonna have rights and lefts. Which ones are bigger? Are the right values bigger or are the left values bigger? It's actually the right values. Imagine like coming all the way over here, like coming all the way to that x coordinate with some, amount. Let's say we went 5 or something, right? And then coming over to this x coordinate, that was a smaller amount. That was like 3, right? So we're always gonna want the right value minus the left value because that'll give us a positive distance. Okay, so right minus left will be the thing you're thinking in your mind for your integrand. And then this is the weird, why it's hard is that your limits of integration are in terms of y, so this has to be a dy. So the horizontal slices have to be in terms of y, and so which means you have to do the extra work of solving the formulas for x's, because that's what we're caring about are these x distances. How far to the right did we go, right? How far here did we go? So we're basically taking that x distance minus this x distance, and that would give us that leftover distance. Okay. So that's the extra work you have to do for horizontals, is you have to figure out what the x coordinates were. So you have to solve these equations for x. Okay. So if this is y equals x cubed over 2, and if anyone came in late, just double check I had an error on that, x cubed instead of just x. Okay. But then solve this guy for x. Right? So multiply both sides by y. So this is like 2y equals x cubed. What should you do to both sides to solve for that x cubed? Cube root. Do you need or should you put a plus or minus? No, because it's a cubed, right? It's only if it's an even, that's when you need plus or minus, right? So this is that x would equal the cube root of 2y. And was this x cubed over 2, would that be like our right function or was that like our left function? If you look in the picture, was this cubed one the one over on the right or the one on the left?
Right.
This was like the right? So there's our right function. So there's our right function. And then this is our left function. Solve this guy for x. So if y equals 2 times x, divide both sides by 2, and so x equals y over 2. And so x equaling y over 2, this is like our left function. And so now we're going to plug that into our formula. We were integrating starting at 0 and going to y. So the area starting at 0 and going to 4. and those were y values, of the right curve, which was cube root of 2y, so cube root of 2y, minus the left curve, which was y over 2, all with respect to y. Now this is the hard, or the continuing to be the hard part about horizontals, is that you can't use the cute little y1 and y2 in your integrand, because if you typed in, you know, this in for y1 and this in for y2, those are in terms of x. Notice here, we have these in terms of y. So this, I suggest you just math 9 and literally type this in, but use x as a dummy variable, just so you don't have to do like alpha y, alpha y. So I'm just gonna write this here. I'm gonna make a note. I'm gonna say type into calculator, but use x as variable, just to make it a little easier. So I'll show you that here, but you literally have to type this in, cube root of, right? Now, what do we know the area of this region is from when we did it the other way? 2, right? The area is still gonna be 2, y'all, right? Now we've just sliced it up different. You know that expression, no matter how you slice it? Like, here it's so appropriate. Like, literally, no matter how you slice it, you're still getting an area of 2, right? So this one's math 9, integrating from 0 to 4. And now this, you have to like literally type in what was sitting there. So cube root of. So if you go second square root, nope, that's not what I wanted. If you go math, that's what it is. Math, go to 4, right? But I need to delete that other one. Delete. Okay, sorry. Math 4, right? That's cube root of. And then you could do 2 alpha y, but I'm just lazy and I just go 2x. So I'm using x as like a dummy variable here. So cube root of 2x and then minus x divided by 2. And if I remember correctly, I think this one gets us really close to 2. It like doesn't know how to tell us it's 2, but it's like 1.99999 or something. There it is. 2.00004. So it'll always be accurate to 3 decimal places like on your AP test, right? If you go all the way here to 3 decimal places, it is 2. If we do it by hand, we're gonna get 2. It's just the calculator, you know, it doesn't know how to perfectly calculate it this way. Is that a question, Katie? Yes.
How are you getting your x button, like on the calculator without messing off the x?
Oh, I love this. Can I teach this to you? There is the cutest little button that says x, t, theta, n. And I love it. By senior year, if you haven't known this, that is the x button. Every time you just literally press that button. Yeah? I know. But it's just so good. Every time you go alpha, alpha.
Oh my
I
god.
know. Every time. I know. At least senior year, February, I taught you something. Okay. That's just X. I know. Did it seem too fancy? I know. Okay, so let's fill this in, y'all. This is, for this whole section, every time we're going to do this. Okay, so vertical slices, y'all. Vertical slices are always perpendicular to the x-axis. So this might feel weird, but we'll talk about the thickness of a slice. So obviously, like, if we slice it, I don't know if you know what I'm saying when I'm saying slice. Like, we're gonna take this region and we're gonna slice things up. Yeah, we're like chopping it, yeah? So we're either slicing vertically or we're slicing horizontally, okay? And so while, you know, I used to use like wiki sticks. I haven't pulled them out this year, but do you know what a wiki stick is? It's like that like sticky yarn. You used to like get it maybe when you were a kid in like a restaurant to keep you busy, and it like sticks together and you like build little like, you know? I'll pull them out, I have them over here after I stop filming. Okay, but like imagine, you know, this is a wiki stick and right next to it is the next wiki stick and the next wiki stick, and it like is creating areas, right? So like in theory there's not thickness, but like if you thought about the tiny little bit of thickness, the point is that this would be like a change in x. Maybe we started right here at 0 and went over to like 0.2. Like the slight thickness of our vertical slice would be a dx. The point being it's a change in x, and so the whole problem is going to be in terms of x. The limits are going to be x values. The function is in terms of x, which means y is solved for. So basically, if you have a vertical slice, it's all about x's. We love this. This is our fave. We like vertical slices. It's less work, right? Which means we solved for y. And usually the problems are given to us and they're solved for y. The hard part, or the like more challenging, are the horizontal slices. That's what we did second there, right? The horizontal slices, if you can imagine, this is where we were slicing it like this way. You know, we're figuring out what the area was, and we're like, have all these slices. So if we just have one slice, and we thought about what the thickness of that slice would be, that would be like a slight change in y. It's like it started here and ended here. So horizontal slices are perpendicular to the y-axis. The thickness of the slice, we would say, is dy. It's like a slight change in y. And then the limits are y values, and the functions are in terms of y. So there's my little asterisk. This is the extra work, right? So here's the extra work that always has to happen for horizontal slices, is that we have to solve the formulas for x. So that was that extra kind of annoying work that we did on that last one where we had to solve for x before we could actually type it into the calculator. Okay. Oh, I forgot to fill this bottom stuff in. So for the vertical slices, when I'm saying think, I'm really thinking, I'm asking you to think about what the height of the slice is, right? So the top of the slice is starting at the top function, and the bottom of the slice is ending at that bottom function. So in not very mathy terms, I want you to think like top minus bottom. So if you have the vertical slice, you're worrying about like what functions on the top, what functions on the bottom. But if you have a horizontal slice, what do I want you to think about? Right minus left. Nice. It's big minus small. It's always just big minus small, right minus left. Okay. Always just big minus small. Oh, and I guess these were my like rules. To find the area between the curves, sketch the region, find all points of intersection, and decide if vertical or horizontal slices. Then write the integrals to find the area. Yeah. Those are the steps. All right, let's see. I'm taking forever here. Let's see what we can do. Is it just these three, or is there more on the next page?
Just these three.
Just these three. Okay, good. I know. These will go quicker though, hopefully. Okay, let R be the region in the first quadrant enclosed by that. So go ahead and use your calculator. Type that in as your Y1. Oh, and this one, I remember, they gave us a cute little picture. So maybe we don't even have to use our calculator for this one. I bet we could figure this out. But we have two graphs. We have f of x equals square root of cosine of x. Not something I'd expect you to know what the graph looks like, right? That's square root is one thing, cosine is one thing, but I don't expect you to know what it looks like together, you know? But I do expect you to know what this one looks like, right? G of x equals e to the x. Nice, right? So what do you think? Is this one right here, do you think that one's the f or the g?
The G.
I think it's the g, right? There's my e to the x. So boom, there's my g of x. Right? Now this looks like a straight line, a straight vertical line over here, right? So if I keep reading, here it is, the vertical line of x equals pi over 2. So vertical line, y'all, pi over 2. If we do a vertical slice, they've just provided our limits of integration for us. Basically, I'm starting here at 0, well, I'm assuming, but let's double check. And if I do a vertical slice, I'm going to keep slicing until I get to pi over 2. So I know that's an issue. Sometimes students want the pi over 2 to be like either the top or the bottom function, but if you do a vertical slice, essentially that's just your limit of integration. Okay. Now, I'm assuming that here at 0 these cross, but I don't have to assume because let's actually test that. G of 0, e to the 0th, I think that's indeed 1, right? And f of 0, square root of cosine of 0. What's cosine of 0? 1, right? Square root of 1 is indeed 1, right? So I have enough knowledge to actually know that yes, indeed, that is touching there at 0, 1. Or I could use my graphing calculator, second trace calc 5, point of intersection, and find those points of intersection. Okay. So for me, I'm going to choose a vertical slice on this because it's nice and consistent the whole entire time. No matter where I slice it, I take the top curve minus the bottom curve, and I can like see my slice in there the whole time. Versus, if I tried to do a horizontal slice, look at how annoying. Down here, it would be pi minus 2 minus that, pi minus 2 minus that. But then right in here, it would switch. And I'd have to go pi minus 2 minus the other curve, pi minus 2 the other curve. It's doable, it's just way more work, right? I'd have to split into 2 regions. So do the easiest version, and usually it's vertical. Okay. So I'm gonna choose vertical. I would integrate from 0 to pi over 2. So 0 to pi over 2. And then the top curve minus the bottom curve. So because they named them cute little names, I'm just gonna say g of x minus f of x. Right? You can actually write the functions in if you'd like, but no need to. Just write the names and then dx. And then from there, you can just type it into your calculator. This is one you would have to use your calculator on. You can't antiderive the square root of cosine by hand. So you'd have to type that in, math 9, integrating from 0 to pi over 2 of y1 minus y2, or the actual curve sitting there. And then what'd y'all get? Did they get anything? I start with a 2. 2 point. Nice. Accurate to 3 decimal places, right? I have 2.612. 2.612. And that one we are not doing the other way because that's annoying. We're not going to do a horizontal on something like that. Yes?
Do you ever have units?
Very rarely have units this unit. Huh. Yeah, no. Like there's not a lot of context to these problems. It's like find the area of these things, find the volume of these things. So good question, but yeah, no, that's kind of nice. Okay, moving on maybe to the next one. You guys don't mind? Let's see this next one. Find the area in the first quadrant bounded by y equals natural log of x, y equals 1, x-axis and y-axis. We'll challenge us to do this one without a calculator. Let's see if you can get the area of the region that you're trying to figure out. So it did say in the first quadrant, right, bounded by. So y equals natural log of x. I saw a lot of y'all know e to the x was this one, right? Natural log is this one, right? It stays in the first and fourth quadrants over here. What's that point? Where does it cross the x-axis? At 1, nice. 1 comma 0, right? So there's natural log. Y equals 1. What kind of line is y equals 1? Horizontal, nice. So y equals 1, boom, is here, right? Y equals 1. It says the x-axis, here's the x-axis, and here's the y-axis, right? Can you guys see the shape that you're working with? It's this little like, I'm just gonna shade it in like this. It's this shape in here. It's that bounded region in here. So that's always like the first thing is like figuring out what the region is. Sometimes that can be challenging. So they told you the x-axis, the y-axis, the curve, and y equals 1. So that's the region. And so now you're, thinking about, do you want to slice this up vertically or horizontally? Those are kind of the two questions, right? So vertical versus horizontal, right? So vertical, if you choose to do vertical, you totally can. Just realize that vertical, you're gonna have to have 2 separate integrals. To the left of that blue squiggly line, you're doing top minus bottom, top minus bottom, top minus bottom. But it's just a cute little rectangle, which is totally fine. And then you have a separate integral, right? So this first one would be from 0 to what? 1, right? Because that's where we stop right there. So from 0 to 1, we'd be integrating 1 minus 0. 1 minus 0 with respect to x. Or you could just literally find the area of that, right? What do you think you're gonna get? If this is 1 and that's 1, it's gonna be 1, right? But you could actually integrate that by hand. And then plus the integral from 1 to e. Nice, honey, that's e, right? We know that that's e because e comma 1, natural log of e is 1. Nice. So integrating from 1 to e. And then what would that one be? Top is 1 minus, what's the bottom curve? Natural log of x, right? Nice. So this time, I think the vertical is maybe a little bit more challenging because you'd have to have 2 separate integrals. But for some of you, that still might be easier. Sometimes vertical, even with 2 integrals, is easier than doing all the work for horizontal. Okay, so that would be one option. You could add that up, get your answer. The other option though, if you notice for horizontal, this one's consistent the entire time. It's always right minus left, right minus left, right minus left, right minus left. We would only need 1 integral if we do horizontal. So there is something to be said for that. So the extra work, if we do horizontal on this, we're gonna have to solve each of the equations for x. So if y equals natural log of x, which hopefully you can see is like the right curve, right? You gotta solve that for x. What would x equal if y is the natural log of x? What's the inverse of natural log? It's that other weird number.
X minus
E, there it is, E. Nice, y'all, e to the x. Remember how e's and natural logs undo each other? They're inverses of each other. So do you remember that natural log really meant log base e? So this would have been e to the, oops, I wrote x equals e to the x. What did I mean? The y, my bad, y'all. Maybe to remind you that this was really y equals log base e of x. And so it's e to the y equals x. So that's gonna be our right curve. Our left curve was the y-axis. What's the equation for the y-axis? What's the equation for the y-axis? X equals 0, nice. So x equals 0, right? Because we want to solve for x for the horizontals. And so the setup on this, the area would just equal the integral from wherever we started to wherever we ended for the y values, 0 to 1. Right? And then the right curve minus the left curve, well, right curve e to the y minus the left curve, which was 0, all with respect to y. This one's almost too tempting not to integrate by hand, y'all. What's the integral of e to the y? E to the y. Evaluated from 0 to 1, plug in the 1 minus plugging in the 0. So plug in the 1 minus plugging in the 0. E to the first is just e. What's e to the 0th? 1. So the area of that region is e minus 1, right? If we did that by hand, e minus 1. If we did it in our calculator, I know y'all know the estimation of e, right? 2.718, nice. So 2.718 minus 1 would be approximately 1.718. Isn't that kind of fun? Either way, no matter how you slice it, right, vertically or horizontally, you should still get the same answer. So if you had typed that in that way, you should have gotten that decimal. Okay. Last but not least, I know we're backing up to lunch here, so you guys probably want to get out of here, but R be the region bounded by this thing there. So if you want to get that typed into your calculator, f of x equals x to the 4th minus 2.3x cubed plus 4. And the horizontal line y equals 4. And it said there is some vertical line, x equals k, right, that divides these two regions with equal area. I think I left off some word right there. Something. Involving integral expressions whose solution gives the value of k. Let me find what that left dot word is. Okay, with equal area. The whole thing actually is left off. Equal area. I'll write it on my little. Equal area. I meant to say right, comma, but do not solve. Right, but do not solve, comma, an equation involving integral expressions whose solution gives the value of k. Okay, so all this being said, right, I bet part A on this actual for your response was something about finding the region of, or the area of region R. Okay, so hopefully you can see that this region is sitting here to find the area of this region. What do you think, vertical or horizontal slices?
Vertical.
Vertical, right? Constantly this line minus the thing, this line minus the curve, right? So vertical slices for sure. And then what this problem is talking about specifically, it said there is some vertical line, x equals k, right, that divides this region perfectly in half. So if you guys had to guess, like, tell me when to stop. Like, when do you think we're like dividing this in half? Like stop-ish, somewhere in here-ish, right? So there is some line, x equals k, where this area on the left was exactly equal to that area on the right. And so it's asking us to write an integral expression that we don't have to solve it, but if we did solve it, we could find k. Okay? So I know class is about to be over, so I'm just going to jot down the answer, right? You would have to first find the points of intersection. So when you find these points of intersection with this line, y equals 4, and this equation here, it ends up being exactly 0 here, and this point over here is 2.3. So this is exactly 2.3. There were no decimals, it was like 2.3000, right? So it wasn't like, I didn't round this, that was exact. And so, you know, the area, if I went from 0 to k, so 0, you know, to this k value of the curve 4 minus the curve f of x, so 4 minus f of x dx, right? That would be exactly equal to the other side of the area, right? The integral from k to 2.3 of 4 minus f of x. Not the only way to solve that problem, by the way. If you had already found the area of the whole region, you could have just had one of them and set it equal to half of the overall region. Okay. And again, you didn't have to solve for k, but you could solve for k if you needed to. All right, y'all, hope that made sense. Bye.